Greetings. I'm Daniel Ospina Acero. I'm a fourth-year PhD student in the Electroscience Lab in the Department of Electrical and Computer Engineering of The Ohio State University. The title of the work is Challenges on the Applicability of Adaptive Relevance Vector Machine for Image Reconstruction in Softfield Tomography. So Softfield tomography usually involves the solution of an inverse problem. An inverse problem is simply the inverse procedure of a forward problem. So an example of a forward problem is simply the case that we see here at the bottom, where we have an image on the left, and through some transformation F, we produce the blurred image on the right. The inverse problem would be to do the opposite or inverse of that, where we take the image on the right and go to the image on the left through some procedure. Naturally, this last procedure is much more difficult because we need to infer all the details of the image from the blurred image. There are two main characteristics of inverse problems. The first characteristic is that the problem is ill-posed, which means that there are infinitely many solutions, essentially. And the second characteristic is that the problem is ill-conditioned, which means that the problem is very prone to numerical instability. Now, Softfield tomography deals with techniques for visualizing or imaging some physical characteristics of a domain from boundary measurements of fields taken at the boundary. Here's a schematic view of that, where we have a domain and we place around it a number of sensing elements, and through some transformations with hardware and software, we obtain a reconstructed image and other derived parameters at the end. A special characteristic of Softfield tomography is that the fields tend to have a self-averaging behavior in the domain, which means that the value of the field at a given point equals the average of the values in its neighborhood. Common examples of Softfield tomography are electrical impedance tomography, where we measure electric potential at the boundaries and we want to reconstruct the conductivity distribution. Or electrical capacitance volume tomography, where we measure electrical capacitance at the boundary and we want to find the permittivity distribution in the domain. Now, the general problem in Softfield tomography can be described as follows. So we have a set of known boundary measurements, which we call T. And we have a set of unknown physical quantities that we call W. And we have a functional relationship between the two that we call F. Now, if the variability of the quantities in W is small, we can effectively achieve a linear approximation through the use of a sensitivity matrix, which we call phi here, that basically measures the amount of change in the quantities in T due to small changes in the quantities in W. Now, if we use this linear problem description, we will see that we will end up with a very underdetermined system of equations, which comes from the original ill-posedness and ill-conditioning of the problem. This means that there are infinitely many vectors W that satisfy the equation, but very few of them represent useful images. Now, in recent years, there have been attempts to reduce the underdetermined nature of the problem via modifications of the original sensor. The idea being to introduce more equations for the same number of unknowns. One way to do this is simply by taking the original setup and placing more sensing elements. And even additionally, in some instances, it's even possible to combine electronically some of those sensing elements to form synthetic sensing elements that can insert stronger interrogating fields. An example of this is, of course, adaptive electrical capacitance volume tomography, which takes the traditional ECVT sensor and splits the capacitance plates into smaller segments to later combine them into synthetic capacitance plates. There are a few challenges with this approach, however. The first challenge is that although we can obtain more information, our sensing elements are much closer together, which means that the measurements are very correlated. So we have now a longer scanning process with very little clarity on how informative each measurement is. The second challenge is that if we use electronic combination, we don't know exactly which sensing elements to combine to achieve good performance in general. So we have problem-dependent tuning. Now, to address these challenges, in the literature, there have been attempts to use the adaptive RVM in different imaging applications. So for instance, the idea there is to adaptively insert measurements into the model through the iterative minimization of uncertainty. With that, we simply select a subset of the most relevant measurements so that we still obtain good performance in terms of image reconstruction and parameter estimation. This, in turn, leads to a speed up of the solution process. Our aim in this work is to show that in certain soft-field tomography scenarios, the use of the adaptive RVM is not always reliably applicable. Now, the adaptive RVM is a procedure that builds upon the original RVM and defines a strategy to adaptively insert data points into the model. Now, the original RVM algorithm is simply a probabilistic algorithm which defines a framework where the posterior random vector, that is W, or the vector of unknowns, given all the known parameters, ends up being Gaussian, with a known mean vector and known covariance matrix sigma, as shown here. Now, it's important here to highlight that our estimate of W ends up being mu, because that's the point that maximizes the posterior distribution. And therefore, our measure of uncertainty in this case is given by sigma, the covariance matrix, taking advantage of the fact that we have a Gaussian distribution. Now, the adaptive RVM then takes the estimate of the covariance matrix sigma and defines a procedure based on the structure of the differential entropy of the posterior and the change that it suffers when a new measurement is inserted into the model. So for instance, if we have here the entropy of the original set of measurements, this is the expression for the new, the entropy that we obtain when a new measurement is inserted into the model. Now, if we want to minimize that expression, we basically need to minimize the expression on the right, which reduces the uncertainty or the variability. But to do that, we have to maximize that term framed by that red rectangle. So this defines an iterative procedure where at every iteration, we seek for the sensitivity vector that maximizes that term in the red rectangle. And then those measurements simply are the ones that are inserted into the model. However, as we show next, the operation of such a procedure in some subfield tomography applications is not very reliable in general. So the first case that we're going to look at is in adaptive electrical capacitance volume tomography, which is simply an extension of the 3D version of electrical capacitance tomography, where we take capacitance measurements taken at the boundary to reconstruct the permittivity distribution in the domain. So as we said earlier, in adaptive electrical capacitance volume tomography, we take an original, the traditional ECVT sensor, and split the capacitance plate into smaller segments, and later we combine them electronically so that we achieve a finer stepped scanning of the domain. So this is the scenario that we are going to use for the numerical exploration, and this on the right is one set of results that we obtain. What we're showing there is the evolution of the entropy as the adaptive RVM process happens. So we see there that we have a decreasing behavior, but that decreasing behavior is not monotonic, which means that at a particular point, we have a defined or a given value of entropy, but the subsequent step can give a higher value of entropy, which means that having more measurements in the model can lead to an increase in uncertainty, not a decrease. So this is counterintuitive, of course, and then this is the first indication that there's something off with the operation of the adaptive RVM in these scenarios. Now, here we have the comparison between the actual entropy that we obtain when we insert a new measurement and the estimate that through the formula that we showed earlier. This is for two different moments of the operation of the adaptive RVM. One when we have 168 measurements and one where we have 1,512 measurements. So we see that in none of the cases, the plots coincide at all, not even when we consider the minimum values in the curves. So this basically signals that the operation of the adaptive RVM, which is completely based on the estimate given by the blue curve, is not reliable in general. And lastly, we have an artificial scenario where we are going to prescribe what the sigma covariance matrix should be a priori, and later we obtain the estimate provided by RVM, and then we compare the two to see how accurate the estimate is. To prescribe what sigma should be, we follow this procedure, and then we obtain exactly the structure that on which the RVM algorithm is based. So this is the scenario that we use for this test, and we evaluate two cases. One that's overdetermined, where we have 5 unknowns and 100 data points, and what we also have another undetermined case where we have 5 unknowns and 4 data points. So we see on the left, the overdetermined case, a good coincidence of all the values or the quantities being compared. The target values, the mean, and the covariance matrix at the bottom. But in the underdetermined case, what we see is that although we have a good agreement in the target values, in the mean, we have some disagreement. And in the covariance matrix, we have considerable disagreement. This is in the underdetermined case, which is the situation that occurs with most subfield tomography applications. And then we see that we have unreliable estimates from RVM. So in conclusion, we have demonstrated through a couple of applications that the adaptive RVM provides inaccurate uncertainty estimates in subfield tomography applications, and thus its use is not very reliable in those instances. Thank you very much.